I'm studying in Sri Venkateswara College of Engineering. My USN IVE 23 ECE 109 course Electronics and Communication. Let's move on to the topic. My topic is Fundamentals of Vector Calculus. Vector calculus is a crucial mathematical tools in physics providing the framework to describe quantities that have both magnitude and direction such as force, velocity and electric fields. Here are some fundamental concepts of vector calculus often used in physics. Vectors. In physics, vectors are quantities that have both magnitude and direction. They are represented geometrically as arrows. Vectors can be added, subtracted, and multiplied by scalars. Vector operation, addition and subtraction. Vectors are subtracted component-wise. For example, given two vectors a of ax, ay, az and b of bx, by, bz. Their sum a plus b is ax plus bx, ay plus by, az plus bz. Scalar multiplication. Multiplying a vector by a scalar changes its magnitude but not its direction. Dot product. The dot product of two vectors a and b is given by a comma b is equal to ax bx plus ay by plus az bz. It gives a scalar quantity and measures the projection of one vector onto another. Cross product. The cross product of two vectors a and b is given by it results in a vector perpendicular to the plane containing a and b and its magnitude is proportional to the area of paragonal formed by two vectors. Gradient. In physics, the gradient of scalar field is a vector field that points the direction of a greatest role of increase of the scalar field that and whose magnitude is the rate of change in its direction. Divergence. In divergence of vector field is a scalar quantity that measures the outward flux of the field from the infinitial region in the space. In physics, it often represents the rate at which a fluid flows out from a region of space. Curl. The curl of a vector field is a vector quantity that measures the rotation or the twirlings of the field around a point. In physics, it often represents the circulation or the tendency of a fluid to rotate at point. Application. Mechanics and kinetics. Vector calculus is used to describe the motion of an object. Classical machines. It helps in analyzing forcing, velocities, acceleration, and trajectories of particles and rigid bodies. Application includes the study of projectile motion, planetary motion, and the dynamics of mechanical systems. Electromagnetization. Vectors calculus is a fundamental to study electromagnetism. Maxwell's equation, which govern the behavior of electric and magnetic field, are exposed using vector calculus. Application include the design of electric circuits, antennas, motors, and generators, as well as the understanding of electromagnetic waves and communication system. Third one, fluid dynamics. Vector calculus is essential in describing the motion of fluids, including liquids and gases. It helps in analyzing fluid flow patterns, measure distribution, and the phenomena. Application include hydrodynamics, weather forecasting, and the design of pipelines, pumps, and aircraft. Quantum machines. Vector calculus plays a role in the quantum mechanics, particularly in the formulation of equation and the description of the wave function. It is understanding the behavior of particles and the quantum level and in predicting their instructions and interactions. Advantages. Unfilled framework, it provides an unfilled framework of description physical quantities that have both magnitude and direction. This always to express the various physical laws and phenomena in the systematic manner. Geometric interruption. Vector quantities can be represented geometrically as arrows in space, making it easier and visualize and understand the physical concepts such as force, velocity, and electrical fields. Mathematical rigor. Vector calculus provides rigorous mathematical tools of analyzing physics system concepts such as gradients, divergence, and curls helps physics formulate the solve problems in mechanics, electromagnetism, and fluid dynamics. Maxwell equation. Vector calculus plays a role in formulating Maxwell equations which describe the behavior and electric magnetic field in space. Those equations are fundamental in understanding electromagnetism, have a wide ranging application in technology including techno-communication and electronics. Fluid dynamics. In fluid dynamics, the vector calculus is used to describe motion of a fluid, including the flow of air and water. Concepts such as divergence and curl help to analyze fluid to flow patterns and understand phenomena such as turbulence and vortex formation. Quantum mechanics. Quantum mechanics, the vector calculus is essential for describing the behavior of particles and fields at the quantum level. It is used for explanation, formulation, and equation in the study of wave function and probability amplitudes. Disadvantages. Complexity. Vector calculus involves mathematical concepts that can be complex and abstract, especially for those who are familiar with advanced mathematics. Mathematical rigor. While vector calculus provides a rigorous mathematical framework, its application can sometimes be challenging due to complexity of equation involved. Solving vector calculus problems often requires computational intensity. Some vector calculus problems can be computationally involved, especially when dealing with large deserts of complex physical systems. Performing calculus involving in divergence and curls may require significant computational resource time. Assumption and approximations. In practical application, physics often needed to make assumption and approximatical simplify vector calculus. Limited applicability. While vector calculus is widely used in classical physics, electromagnetism, and fluid dynamics, it is applicable may limited in certain areas. Interruption challenges. While vector calculus provides a powerful mathematical language for describing physical phenomena, interrupting the results of vector calculus. Thank you.